Okay, so we are July 20th, so we are right here. And I'm not sure, so we might even make it to relations today, but if we get that far, I might stop. So it might be a bit shorter. The reason being, I think it works better when each topic is contained within one lecture. And when I start splitting them up, because a lot of you are consuming it via the videos, and then when I start splitting them up, I think that makes it more confusing as to where you can, update yourself or on a certain topic. So we'll see what happens though. Because if the lecture is only an hour and a half, then we'll probably get started on relations as well. And the other thing is quiz 3 is this week. So it's a little bit different. There's only one link. Everybody should be able to click on the same link, and it'll give you the correct amount of time. And then, so things are pretty tight for the end of the year. Not too tight, but so assignment 4 is actually going to be 2 weeks from today. So that's a little bit tighter than usual. I've cut a couple of the questions, but I couldn't cut too many because I have to cover a certain amount of material. So just be aware of that. Don't delay getting started on that. And then the week after that is quiz 4. That's in the final week. I don't think quiz 4 is particularly hard, but we will see. Assignment 3 is due. So good. Any questions on our schedule or anything else? Okay, so we're going to pick up where we left off last week. I do have a question. Any news on the final? No. So I know they asked me what kind of final I was having. So they are I guess making the schedule right now, but they don't. I haven't seen the schedule posted. I haven't got any unofficial schedule, so I don't know when the final is. I do know that it's going to be similar to the quizzes. You'll have a few days in which to do it, and one of those days will be the day that it's actually assigned or scheduled for. So there is a bit of flexibility there if you're trying to make plans, but again, I don't know anything about the exact date at this time. So unfortunately, it should be coming up soon. I'm guessing maybe by the end of this week or early next week. Okay, any other questions? Okay, so let's do. Where'd my lesson go? Sorry. Sorry, I seem to have misplaced my lesson. What the heck? Okay, that's really weird. Oh, here we go. Oh, geez. All right, found it. Okay, so I'm going to pick up where we left off last week. So last week we were talking about Big O notation. So we had started, we had a small introduction to functions, just to sort of, so you knew enough about functions that Big O wouldn't be completely confusing. And then we started Big O, and so we didn't get to Big Omega. But I'm going to review Big O a little bit. So here is actually the definition of Big O. So what we want to do is bound functions, and specifically we want to bound the growth of functions. And this, applies to computer science in terms of, well, we just looked at how to analyze an algorithm and how to count operations. But typically when we talk about algorithms in computer science, we do talk about Big O notation. So we say an algorithm is Big O of n squared. So that might be, something that takes quadratic time. So we use Big O and Big Omega a lot in computer science, and it sort of relates back directly to analyzing these algorithms. So yeah, so f and g are functions. Functions are simply actually, maybe we can review that a little bit. So a function is a mapping from a set of inputs to a set of outputs, generally speaking. And we can sort of look at an analogy in a function in a computer program. So in this case, it's the Gregorian calendar, and the function is, if we enter a year, the function tells us if it's a leap year or not. So this is the pseudocode for that, and then so we have a set of inputs and we have a set of outputs, and the set of inputs is, any admissible year on the Gregorian calendar. And the set of outputs is either true or false. And then what makes it a function specifically is how we map the elements. And how we map the elements is that for any given input, so if I take this input, I have exactly one output. So if I input 1583, I get back false every time. And I don't get back sometimes true or anything ambiguous. I put in 1583, I get back false. So that's the definition, roughly speaking, of a function. The other part of it is that for every element in A must be mapped to something in B for a function from A to B to be valid. So that's that, and it's functionally a lot like computer programming functions, a Python function. Yeah, so it's an assignment of exactly one element from the set B to each element of the set A, right? So that means for any given input, I have exactly one output. And yeah, another way to test for a function is if I plot it out, whereas this is the input and this is the output. Then if I draw a vertical line, it should intersect the plot at only one place. So that's a sort of an alternate definition of function. Although functions are more general because they're from a set to a set, but yeah, this is when we're talking about functions that sort of mirror a math expression, the vertical line test is a good test of whether or not it's actually a function. Okay, and the rate of growth of a function is typically determined by it is determined by the highest order term. How we rank the highest orders is yeah, sort of predetermined. Yeah, and we've seen all this is sort of review. We saw how the different changes result in the different complexities. So we're really more concerned with, the size of the exponent more so than anything else. And the size of the exponent on the highest order term, that's going to make the biggest difference in terms of how quickly our algorithm runs. All right, so this is all sort of review of last week, and we saw this is a visual example of all these functions plotted out and how, x to the cubed really just dominates anything that's an order of magnitude less. So anything that's quadratic is dominated by x cubed. So yeah, that brings us to the big O notation. And so specifically the big O notation is, we say f at x, which is a function, is big O of g of x, which is another function. These are functions from the integers to the real numbers or the real numbers to the real numbers. So f of x is big O of g of x if there exists constants c and k such that both of them are greater than 0. And for all x greater than or equal to k, f of x is greater than or equal to 0 and less than or equal to some constant times g of x. And so f of x said to be big O of g of x, or equivalently, f of x is a member of the set of big O of g of x. So we never really use the set notation with big O, even though it is when I say O of some function, in this case g of x, this is a set of functions. So it is more proper to use the function, the set membership, but typically we use equals, and or you know, it's grown to be very informal at this point. And so our C and our K values are said to be witnesses. So we'll do a couple quick examples, or redo a couple quick examples from last time. And then I'm going to show you actually, so I'm going to resolve one question from the last lecture, and then I'm going to show you how to do big O with limits, which is actually, it's a little bit different. It's much easier using limits to prove something is not big O of something. So that's going to be nice and sort of convenient for your assignments. So yeah, when I say f of x is big O of g of x, then g of x is sort of an upper bound on the growth of f of x. And we can see that here. If we have f of x equal to x squared plus 200, then we can choose k equals 15 and c equals 2. And so this is 2 times x squared here, and this is x squared plus 200. So we can see that the orange line is an upper bound on the blue line after this value here, which is sort of what you want k to be, although k could be anywhere past that point. So anywhere to the right of that point. So k could also be here. That's fine. As long as k exists, that's what we're concerned about. There is a point where these two paths cross, and forever afterwards, then the orange line is above the blue line. Is c always 1 greater than the leading coefficient of the function? Not necessarily, but in a lot of cases it is. And so we're going to look at actually the cases where it is and where it isn't. C can be equal to the leading coefficient if all your other terms are negative, for instance. Then that's sort of very easy to prove. And in fact, you asked if C is always 1 greater than the leading coefficient. C can actually be, you know, 0.1 greater than the leading coefficient. And then there's still going to be some k for which there's going to be a k that exists at which that f of x is big O of g of x. So we'll see some of that. So yes and no, I guess. All right, so how would we show that there's an upper bound? Yeah, this is stuff that we saw last week. But in this case, if we have this, if we take this function, then we can say that it's less than or equal to, we can drop this negative term. So when x is greater than 0, this expression is less than or equal to this expression. And then we can say, well, when x is greater than or equal to 10, this expression is less than this expression. And so this is less than this when for all x greater than or equal to 10. And so that's how we can find our k and our c values. So here our c is going to be 4, and our k is going to be 10 because, well, this is the constant that we came to, and we decided, or we figured out that it was true whenever x was greater than or equal to 10. So that's sort of a very informal way, in one way to easily find a c and a k. Yeah, so is that clear for everyone? Is there any questions on? We're going to do a couple more examples, but then I'm going to get into limits. So if this isn't clear, let me know. All right. So actually, this is another example from last lecture. And this is, if I did this really formally, so I am in fact proving this. This is a proof. But we, so if I did it all formally, yes, I'm going to post this. It was not in the folder. Yeah, it was not in the folder because it was, I thought about putting it there, but it's still incomplete because the big theta or the big omega and the big theta sections are not complete. So I didn't put it in there yet. There should be a set of slides that are roughly equivalent to this, but yeah, I will post these after today because they'll be, at which point they'll be complete. So this is, if I formally go through this, so I have this definition of big O notation, and it's an if and only if. So if I can prove that there exists, so if I can prove that this part here is true, then because this is an if and only if, this means that f of x is big O of x squared, right? So if this is true on the right-hand side, then the left-hand side must be true also. So specifically, I want to prove in this case that the right-hand side is true. And so this is the very, very formal way to go through it. But as I mentioned last week, you don't have to go through that. You can write it informally, as we see in this box here. So this is my function, and I could say that that's less than or equal to, so 5x squared plus 10x plus 3 is less than or equal to 5x squared plus 10x squared plus 3x squared when x is greater than or equal to 1. So this function is less than or equal to 18x squared just by summing up all these parts, the 5 plus the 10 plus the 3. So then I can declare that, well, this function here is big O of x squared because I have the c and this k value as witnesses. All right, so on an assignment, what's in this box is sufficient. Although what we're sort of saying informally is all of this up here, but we're not going to do big O too formally, simply because this is all just boilerplate. You'd be rewriting the same things over and over again, and what I'm interested in really is that you understand how to prove this. And I'm not really interested in if you remember every single boilerplate thing that you're supposed to write. Okay. And also, yeah, the other thing we looked at is actually this 5x squared plus 10x plus 3 is big O of x cubed. You can simply do the same steps, but then in the final step, we bump up the value of the polynomial from x squared to x cubed. But that's not as useful, and typically we do make use of it, but it's not. If I asked you the runtime of an algorithm and you told me, oh, it's O of x cubed when it's big O of x squared, actually, then that's a little bit deceiving. So. And yeah, so here we'll go through this quick example just as a refresher. So is 3x squared plus 2x plus 1 big O of x squared? Well, we can just say that is less than or equal to 3x squared plus 2x squared plus x squared for all x greater than or equal to 1. So don't forget to make sure that when you're making these statements that you put the proper bounds on the variables. So that's less than or equal to 6x squared. And then so my k value comes from whatever I had to put here, and my c value comes from whatever my leading constant ends up being. So we can say that this function is big O of x squared with c equals 6 and k equals 1 as witnesses. Okay, so and that's a very simple, straightforward example of how we do the big O notation. That's sort of the easiest, one of the easiest examples. Yeah, and okay, so we can do a second one really quickly. So 6x cubed minus 8x squared is less than or equal to 6x cubed for all x greater than or equal to 1. So we can just drop the negative term. 6x cubed minus 8x squared is big O of x cubed with c equal to 6 and k equal to 1. Okay, so that should be hopefully very straightforward. There be any time where the k value changes? From 1, you mean? So you can choose different k values. Let's see here. Yeah, so technically I could do something like, in particular up here, instead of going with c equal to 6, I could choose, well, I could choose c equal to 4, and then I would need some k value, where 4 times x squared is greater than 4 times x squared is greater than or equal to 3x squared plus 2x plus 1. So if I solve this for x, then that would give me my k value, right? So and even if I just, I mean, I could easily take k equal to 10, for instance. So if I solve this with k equal to 10, I get 400 is greater than or equal to 300 plus 20 plus 1, which is true. 400 is greater than or equal to 321. So I could take c equal to 4 and k equal to 10 as witnesses. That works also. Yeah, it's generally easy, especially on these simple functions, to keep it as simple as possible. If you can get away with k equal to 1, then that's what you would do. So you'll see when we do big omega that you can't always get away with k equal to 1. But let's think about this. What if I took c equal to 3? Does that work? So for this function here, this 3x squared plus 2x plus 1, if I take c equal to 3 and k equal to, I don't know, something, is there a k that I can make this true? Right. So you can't, because these two terms are positive. So no matter what, there's no value of k where 3x squared is greater than or equal to 3x squared plus 2x plus 1. When x is positive or greater than 1. X squared. So yeah, you can rule out certain values of c right away, and then technically, so what if I did c equal to 3.0001? Is there a k value for that? So now this is sort of getting a little bit advanced. But yeah, so there's always going to be, as long as I have a c value that's sort of greater than the constant on my highest. Yeah, because that highest order term grows way faster than everything else. There's always going to be a k value. So yes, this k exists. Of course, on an assignment, I want you to actually provide me with a k. But we're going to see a method to do this where we can actually, sort of do this, where we say, yes, k exists. I don't know what it is, but I know it's there. And that's when we use the limits. Yeah, all right. So before we get into the limits, though, so I want to get back to this example. So this is some arbitrary function with, so this is the highest order coefficient is x to the power of n, and then this an is a constant, and an minus 1 is a constant. And these constants can be negative, they can be 0, or they can be positive. And we'll just assume that an is greater than 0. Otherwise, we would choose a lower value for this first highest order term. Actually, we would actually more accurate to do this, but I don't want to. So we don't really see these negative growing functions in computer science. So technically, all the things that we talked about, we should be applying the absolute value to these functions, but we don't in computer science because we don't really have anything that everything takes positive amount of time. There's nothing that takes a negative amount of time. So, and so we talked about how we could find some general constant by taking the absolute value of each of these constants and then multiplying by the highest order term. And then we said that, so we take C equal to this and K equal to 1. And somebody mentioned, well, is that necessarily true? Because that doesn't guarantee that 0 is less than or equal to f of x. And so I forget who that person was, but that person is correct. So actually, we don't know the K in this point, but we know that K exists. So yeah, you would have to actually, this is sort of a quick and dirty way to get a constant, but you still perhaps need to find a value for K where this whole thing turns positive. So that's, so one of the ways we can overcome that is by using limits. So limits are sort of an alternate definition of big O. But before we get to that alternate definition, let's just look at, so what do we mean by when we say limits? So I can take some function and I can take the limit as x goes to infinity of, for instance, 1 over x. So does anybody know what that's equal to? So yeah, it is in fact equal to 0. And in fact, any function that approaches infinity, if I take the inverse of it, then the limit as it approaches infinity is 0. So even if I did, say for instance, the limit of x equals, or x is going to infinity of 1 over log n, or log x, I mean. So even though log x is a slowly growing function, it does reach infinity. So this is actually also equal to 0. Even though it's growing slow, it always increases. So yeah, it never, there's no limit. It doesn't converge on a constant. When I take the inverse, it's equal to 0. So that's what I mean by limits. And I can say things like limit as x approaches infinity of x over x squared, for instance. Now this is, I mean, it's simple. You could cancel it out. But if we wanted to generalize this, we could just say anything where the bottom function grows faster than the top function is equal to 0. So in this case, you know, we could easily have canceled it out and said the limit, this is equal to the limit as x approaches infinity of 1 over x. And so that's what we know to be 0. But then there's another trick, and I don't expect you to know this. So here, this is sort of the ranking of all of our functions, right? So if I did something like, if I took the limit, and I know I'm using n here, but I'm using x over here, so just bear with me. So if I said n log n over n squared, or sorry, I should say x squared. All right, let's do n then. You can just use this ranking without proving anything and say, well, that's equal to 0, because the n squared grows much, much faster than n log n, even though they both reach infinity. So that's as much as I expect from you, is just to know sort of the relative ranking of these coefficients or these terms. But I mean, you could actually prove it using and this is, again, I'm not expecting you to know this, but if I did say something like log n over, log x over x, so it's enough to say that this is equal to 0, but I could actually prove it by using L'Hopital's rule. So which means, because both of these terms approach infinity, so if I take the derivative of both of them, so this is equal to the limit as x approaches infinity of the derivative of log x over the derivative of x. And so this is equal to, so the derivative of log x is 1 over x times, if it's some constant. It's some constant that has to do with the natural logarithm. I don't remember off the top of my head. And then the derivative of x is simply 1. So we get 1 over x, which as we know is 0. So you can use, using the limits, you can figure out these. So we had an extra long proof of how to do, we had to prove log x is big O of x. And that was an actual long proof, and this is actually the same proof, but much shorter, using limits. Okay. Anyway, yeah, that's a little bit of extra background that you don't need, but you should, in general, understand what I'm doing when I have a limit. So, any questions on what limits are? I'm going to show you in a second how to use them to prove big O, but any questions about limits themselves? All right. So then this alternate definition of big O is that a function f of x is big O of g of x if the limit of f of x over g of x is less than some constant c. And an alternate and equivalent definition is to say that the limit as x approaches infinity of f of x over g of x is not equal to infinity. Those are basically equivalent, but they're actually, so this is good for proving, this one's good for proving something is big O, and this is good for proving not big O, as we'll see. And yeah, the one thing, so I'm choosing to use this less than definition. And whereas when I use the C and the K values, I use this less than or equal to. The thing is, the less than is consistent with the previous definition in the sense that if I do find this limit, and I'll show you in a second how, then this C is the same as this C. What I'm basically showing here is that there does exist some K. So anyway, yeah, it's just a small point, but sort of important. Okay, so let's go through an example. So I'm going to show that this is big O of x squared by using limits. So, so I take the limit as x approaches infinity of 3x squared minus 2x plus 20 over x squared. And then I can cancel out some of the terms. So this is 3 minus 2 over x plus 20 over x squared. And then this approach, as x approaches infinity, this term approaches 0 and this term approaches 0. So this is just equal to 3. So then this is big O of x squared if yeah, f of x is O of g of x if and only if f of x over g of x, sorry, the limit as x approaches infinity of f of x over g of x is less than some constant. So here I showed that it's equal to 3, so I can choose a constant 4, for instance. So let me see here. So therefore, 3x squared minus 2x plus 20 is big O of x squared with c equal to 4. And then we know there exists some k value. So we've sent x to infinity, and somewhere along the way, those two functions crossed so that g of x was above f of x. So then in this case, we only need the c value. But this implies that there exists some k such that for all x greater than or equal to k, etc. This definition implies the other definition. Okay, so in many ways, limits are easier to use, but they can also be tricky sometimes. I don't think we're going to get into any actual instances of tricky limits, but all right. So this is, any questions? All right. So let's do another example. So this is big O of x squared if and only if if we take the limit as x approaches infinity of f of x over g of x, and it's less than c. All right, so we're going to prove that. So we take 5x squared plus 2x plus 20 over x squared less than c. And then we can, let's do it sort of more completely this time, plus 20 over x squared less than c. And so this is 5 plus 2 over x plus 20. Sorry, this should be the limit as x approaches infinity. And x squared less than c. So then we get 5 plus 0 less than c. So we can choose c equal to 6, for instance. So therefore, 5x squared plus 2x plus 20 is big O of x squared with c equal to 6. All right, so that's another way to prove big O. And so we've seen it prove big O, but let's see it disprove big O. So is 6x cubed plus 3x big O of x squared? So it is big O of x squared, 6x, sorry. Yes, you technically could say c equals 5.0001. As we talked about earlier, because we can always find a k value that makes that true, as long as it's bigger than the constant on the highest order term. That's the way these, simply because that highest order term is growing faster than the other order terms. So there's always some value where I can can have exactly the distance between them that I want. Okay, so then, yeah, 6x cubed plus 3x is O of x squared if and only if at the limit as x approaches infinity, f of x over g of x is less than c. And recall, I haven't been putting it in there, but c has to be strictly greater than 0. The alternate definition of that is here. If it's not equal to infinity, but so it's also true. Sorry, yeah, we don't need this part for here. This is this comes into play in the big omega. So the other the alternate definition instead of this part is I can substitute this and say, well, it's not equal to infinity. So now if I take the limit as x approaches infinity of 6x cubed plus 3x over x squared, and if I assume that it's true, then I assume that there's some value c for which it's true, but once I cancel out my terms, I get 6x plus 3 over x less than c. And the limit of this is actually infinity less than c, which is false. So it's very easy to disprove. And in big O, it's actually not that hard to disprove anyway, but this is easier. Another way to write it is just to say that if we use this definition, so this is proving it using definition 1, let's say. But if I use definition 2, then I could say prove it directly. Without assuming that it's true, I just say the limit plus 3x x squared equals the limit of 6x plus 3 over x equals infinity, and the definition is that it's should be not equal to infinity. So yeah, those are logically equivalent ways to express that. So yeah, therefore 6x cubed plus 3x is not big O of x squared. And that's easier to prove using limits than using the c and the k values. The c and the k values, you have to instantiate things, and it gets complicated. Well, not complicated, but it's more involved than using the limits. You don't need to know both methods. You can use the c and the k method. Let me think here. I can show you how to prove this using the other method. So when you want to prove something is big O, you know, either method works great. When you want to prove something is not big O of something, then the limit method works better. If I wanted to prove this using C and K, I would say something like, I would use a proof by contradiction. So let's, yeah, let's prove 6x cubed plus 3x it's not big O of x squared, using a proof by contradiction. And then I'm going to use the old method. So I'm going to assume that the old method states that assume 6x cubed plus 3x is big O of x squared. And this is true if and only if there exists C and K greater than 0, such that for all x greater than or equal to K, f, or let's just use the actual function, 6x cubed plus 3x is less than or equal to C times x squared. So this is proving it's not true using the old definition. So I'm assuming it's true. So specifically, I'm assuming this is true, that there exists the C and the K such that I can. So let's write that out. So I'm assuming this part is true for all x greater than or equal to K. 6x cubed plus 3x is less than or equal to C times x squared. So now I'm going to do some, so this is our assumption. So now I'm going to say, well, I'm going to use existential instantiation and say, well, there exists some K such that 6x cubed plus 3x is less than or equal to A times x squared. So this is, I've instantiated the C value, existential instantiation. And now I'm going to instantiate the K value, and you can do both of these in one step, but just to be perfectly clear about everything, I'm going to say for all x greater than or equal to some value B, 6x cubed plus 3x is less than or equal to A times x squared. And that's again this existential instantiation. Okay, so then I can do a little bit of math. I can divide both sides by x squared. So 6x plus 3 over x is less than or equal to A. That's simply math. Now let's see if I remember this final step here. So if I pick, so I say for all x greater than or equal to B, so I can choose using universal instantiation of my x value. I can say, well, 6 times A plus 3 over A is less than or equal to A. So I can choose my B value to be, or I can choose my X value to be at least A in this case. So now I've clearly reached a contradiction since 6A, no matter how big A is, this term will only approach 0. So I'm left with 6A less than or equal to A, which is false. Okay, so I've reached a contradiction. So therefore 6x cubed plus 3x is not big O of x squared. Okay, so if you're not using limits and you want to prove something is not big O of something, then this is the approach that you would use. So it's as I said, it's a bit more involved, but yeah, you do have to prove that there exists this value that I can assign to x that makes this part false. Okay. Good. Any questions on that? So technically, you can just stick with the other method. But somebody did mention limits last lecture, and I also thought it's a nice way to prove prove something is not big O of something very simply. So in this case, I had to use all of this sort of machinery, whereas in the other case, I just, you know, I said infinity less than C, and I get false, and then I'm done at that point. Yeah, I mean, it is a bit more work, and you don't have to, you know, if you skip the existential instantiation, you still need to do sort of the, maybe at the end of the day, it's the same thing. So basically this step is the key, right? Step number 4. You have to substitute some value in for your X. And usually it's going to be, you know, you'll include A in it because X can be as big as you like. So you're going to choose some value for that X that's going to make this left-hand side greater or greater than the right-hand side. So then you get that contradiction. The rest, I don't really mind if you skip the existential instantiations and just jump right into proving that mathematically. So that's sort of what I did here. So maybe at the end of the day, they're about similar complexity, but yeah. Again, really the part I'm looking for is this part, step 4, from step 4 to 5. So choosing that correct value, and then reaching that contradiction. And that's really the same thing we did up here, except it happened for us because we realized that you know, when we take limits, we ended up with this infinity, and then it was pretty clear we don't have to choose. Do we know that A is greater than or equal to B? Yeah, so no, yeah, that's technically another tripping point. You could say that I can take, instead of taking X equal to A, I could take X equal to max of A or B, right? So then I know that it's at least A, so then this inequality is still going to be false. So yeah, technically, if I wanted to be very, very detailed, I should have done this. I am making an assumption that A is at least B, which is not necessarily true, but it's still, you know, logically we would still go through basically the same steps that, you know, we choose some value for X that's at least A, then we still get this inequality here, so it'll still work. Good. Any other questions? All right. So this is actually, so these are examples from last week. But I wanted to stick this in here so when we have when I print out the notes and upload them, that these are in their correct location, these proofs here. So we're going to skip over this stuff. This is just some analysis of functions we did, some common functions. For instance, we showed that x factorial is big O of x to the power x. And the most important one we showed was that log of n is big O of n. And so we just showed that again with using limits and L'Hopital's rule. So you can, well, actually, I didn't do that explicitly, I guess, but yeah, the limit of log n over n as n approaches infinity is equal to, if I take the derivative of the top and the derivative of the bottom, that's L'Hopital's rule. So log n prime over n prime, which is equal to 1 over n times some constant. Sorry, this should be the limit of 1 over n. Equals 0. So that's Yeah, so it's not equal to infinity, so it's and it's less than some constant. Technically, 0 is less than c, where c is greater than 0. So this matches the definition of big O. Okay. Yeah. So this is sort of what I just sort of informally ran through up above. And this is again review from last week, saying the base of the logarithm doesn't matter because it's only going to be different by a constant. And this is the theoretical performances that you saw above. So if you are going to use limits, then you want to take note of the order of these expressions. So that's the so going from here, O of 1 is technically big O of log of n is O of n, etc. This is sort of a transitive relation, even though we didn't really get into transitive yet. Okay, good. Any other questions on that? All right, so we're going to move into big omega, which is very similar to big O, but now we're going to have a lower bound on these functions. So using the traditional C and K method, so using our witnesses, so f of x is big omega of g of x if there exists C and K both greater than 0, such that for all x greater than or equal to k, we have our functions are greater than 0, but that C of x is less than or equal, or C of g of x is less than or equal to f of x. So f of x is said to be big omega of g of x, right? And so this is sort of big O is an upper bound on our f of x, and big omega is a lower bound on our f of x. Right? And basically what that means is that after a certain size of the problem has been reached, f of x is always greater than some constant multiple of g of x. And g of x is a lower bound. But it is a little bit trickier to express big omega in some cases. For instance, if we look at this function here, so we have f of x is equal to x squared minus 100x plus 100. Did I write that wrong? Sorry, one sec. No, that's fine. So is f of x big omega of x squared? So now we want some function that's going to bound this from underneath. But the problem is this function starts out by decreasing, right? So initially it decreases and then it turns at this point and starts going up. And so when if I want to say that this is big omega of x squared, well, x squared actually starts at 0 and sort of goes up like that. So we want to find, it's sort of trickier to find this k value for these big omegas when part of the expression is negative. So typically what we're gonna do is we're gonna find some constant that crosses it like this. All right. So f of x is O of x. This should be omega. It's big omega of x squared if there exists C and K such that C times x squared is less than or equal to f of x. So we want x squared minus 100 x plus 100 is greater than or equal to C times x squared. For some value k. So this is what we want to prove. For x greater than or equal to some k. But it's not as straightforward because we have this negative component. So what we want to do is we want to find some value of k where this function has turned positive. So what we can do is we can split up our highest term. So I can say 1/2, or let's say x squared over 2 plus x squared over 2 minus 100x plus 100 is greater than or equal to some constant times x squared for all x greater than or equal to k. So now what I want to do is find some value of k that makes this part here positive. So let's take, for instance, let's try k equal to 200. So for all x greater than or equal to 200, we're going to say that this term here is positive. So let's say, so let's do it as sort of an aside here. So x squared over 2 minus 100x plus 100 is greater than or equal to 0. This is what we want. For x, let's actually make this for all x greater than or equal to k. So if I substitute the k value in there, I get 200 times 200 over 2 minus 100 times 200 plus 100. It's greater than or equal to 0. So this 2 divides out the 200. So I get this 100 times 200 minus 100 times 200 plus 100 is greater than or equal to 0. So I get 100 is greater than or equal to 0. So that means for all x, let's see. So for all x greater than or equal to 200, x squared over 2 minus 100x plus 100 is greater than or equal to 0. So this is just how I arrived at that number. You don't need to include that necessarily in your proofs. Actually, it would be better if you did prove that explicitly. So that means x squared over 2 is greater than x squared, or sorry, less than let me think here. Yeah. So that means x squared plus x squared over 2 minus 100x plus 100 is greater than x squared over 2, which is greater than 1/2 times x squared. So we found our constant c by trying our constant k that made this term positive. Yeah, I think you should be able to use the quadratic formula in this case. Although, you know, guess and check is perfectly sufficient if you don't want to go through the process of using a square root. You know, you can take some absurdly large value of k, but if you want to use the quadratic formula, you definitely can. So you can find the roots and then, yeah. So therefore, x squared minus 100x plus 100 is big omega of x squared with c equal to 1/2 and k equal to 200. Okay, so that's using the c and k method, and a negative term using on these omegas, which is a little bit trickier, but that's how you would determine that this expression is big omega of x squared. And here we can see, so I graphed it out for k equal to 200 and c equal to 1/2. So this is actually where they cross, but we selected the k being 200. So it's somewhere here. So this is our k value. And so anywhere past the k value, this is a lower bound on this. This orange function is a lower bound on this blue function. Okay. And here's just the same thing, but up to 500 on the size of x. So this should be x. Okay. So any questions on that? That's as tricky as probably the big O notation gets. Is that big omega with a negative term? That's where everything else is sort of straightforward, but there it can get a little bit tricky. Okay. So we have a function here, 4x squared minus 3x plus 6. So we're saying that it's, so we're asking if we can say that this function is big omega of x squared with constant c of 5 and k equal to 6. So are those valid? And why or why not? So let's recall what that means, eh? So so 4x squared minus 3x plus 6 is big omega of x squared if and only if there exists c and k such that for all x greater than or equal to k, 4x squared minus 3x plus 6 is greater than or equal to c times x squared. And in this case, the c is 5 times x squared. So does anybody see the problem with that? Yeah, you can't. And the reason, and this is sort of parallel to the big O that we saw earlier, yeah, the 5x squared, this is, for some value, this is actually going to be always bigger than our function. So choosing the wrong value of c, sometimes you can eliminate cases just at a glance, right? So with big omega, it's if c is less than this, and with big O, it's if c is, sorry, with big omega, it's if c is greater than the highest order term, the constant in front of the highest order term, and with big O, it's if c is less than the constant in front of the highest order term. So yeah, that's you know, just a simple sanity check that you can do to eliminate. Omega is the best case since it's the lower bound. Yeah, it's, well, I'm not sure what you mean by best case. It's, oh, in the sense that, yeah, you could say it's the best case. You don't necessarily know that that's true, right? Because I can, in fact, I could say that 4x squared minus 3x plus 6 is big omega of x. All right, so I can choose some, but actually before we do that, first let's prove this, that this is actually big omega. So this should be kind of an easier case. So it's big omega if it's greater than or equal to some c x squared for all x greater than or equal to k. So we want to prove that that's true. So in this case, it's actually rather simple. I could say x squared plus 3x squared minus 3x plus 6 greater than or equal to cx squared for all x greater than or equal to k. So now I can take this and take x greater than or equal to 1. So x squared plus 3x squared minus 3x plus 6 is greater than or equal to x squared for all x greater than or equal to 1, right? Because when x is greater than or equal to 1, this is definitely positive. So this is sort of the easy case where I can take the highest order term and divide it up sort of easily to cancel out my negatives. So then 4x squared minus 3x plus 6 is greater than, is big omega of x squared with c equal to 1 and k equal to 1. And if I wanted to say that, actually, if I wanted to prove that 4x cubed or 4x squared minus 3x plus 6 is big omega of x, then I could just simply at this point say that the x squared is greater than x. And I have basically the same proof with the same witnesses. So our c and k values are still 1, but now I've proven this instead. All right, so it's straightforward to prove lower bounds that, again, aren't tight. The same with as we did with upper bounds. So we could say that, you know, in the best case, your program is going to run in, if you had a tight lower bound, you could say, well, in the best case, your program is going to run in x squared time. And that's sort of accurate. But if you don't have a tight lower bound, then you could say, well, in the best case, it's going to run in order x time, which is sort of true, but not really true in a useful sense, right? It's not telling me, it's not giving me enough information. Yeah, okay. And now we can use big omega using limits. Again, you don't have to know this. You might find it easier to do certain operations using the limits. Totally up to you. If you just know the C and the K version, then that's sufficient for this class. But I'll show you this because it does make certain things easier. So in this case, so f of x is big omega of g of x if and only if we take the limit as x goes to infinity of f of x over g of x, and it's strictly greater than some constant c. And an equivalent definition is that f of x is big omega of g of x if and only if the limit as x approaches infinity of f of x over g of x is not equal to 0. So these are equivalent definitions. And again, we don't want to use this greater than or equal to simply because this makes it inconsistent with our other definition. So it's technically not incorrect to say this, but I prefer not to do it. I want our two definitions that we use to be consistent. So when we have the C and the K explicitly. So then let's prove this using the limits. So this is big omega of x squared if the limit as x approaches infinity of f of x over g of x is greater than some constant c. So we take the limit x squared over x squared minus 200x. So we'll cancel those. Actually, we'll cancel them after. plus 100 over x squared. It's greater than some c. Infinity of 1 minus 200 over x plus 100 over x squared, which is 1 greater than c. So then we could take, so this is consistent, we can take c equal to 1/2. But we could actually take c equal to 0.9 if we want. Because we know as x approaches infinity, there is some k value. That's what this limit is really saying. It's an existence proof. If you recall back when we did proofs, we're saying we can prove with this method that we know there's some k exists. We don't know what it is, but we know it's there because we've proven it using this sort of, I guess loosely speaking, calculus. Okay. So therefore, but yeah, this is actually this is actually a different function than I used before. I accidentally put 200 here, but it's the principle is the same behind it. If I put 100 there, the 100 over x is still going to approach 0. So, okay. And this is, all right. So I think before we finish this part, I'm going to take a break here. So we'll come back at, we'll take a 10-minute break, unless somebody has questions right now. Okay. So we'll come back at 7:04 and then continue with this. And this is nearly done. And then we'll move into functions. All right. Okay, so we're back. All right, any questions? Anybody think of any questions over the break? All right, so I'm going to take you through, so here's another example where um, you can sort of find through inspection the values for C and K. So as long as we take some C value less than the constant in front of the highest order term, in this case we took 0.8, then we can find some K value. So, you know, if I solved x squared minus 2x greater than or equal to 0.8x squared, and then I took my guess of K equal to 10. So if x is at least 10, then this is 100 minus 20 greater than or equal to 80, which is 80 is greater than or equal to 80. So this is true when x is greater than or equal to 10. So yeah, that's, you can sometimes just through simple inspection prove these things. Okay, so here's a few more examples. I mean, I could run through them if you like. There is one specific example I want to run through, and that's, so we've shown basically when something is not big O of something else. So if, in this case, 3 of x squared is not big O of x squared, or 3 of x cubed is not big O of x squared. And we've shown you how to do that. So I've shown you how to do that. I haven't shown you how to prove, for instance, that 3x plus 1 so it's not big omega of x squared, but we have not run through an example that shows that yet. So so let's run through that. So if and only if there exists C and K, where for all x greater than or equal to K, 3x plus 1 is greater than or equal to C times x squared. Okay, so then we want to prove this part. It's false, obviously, but we're going to assume it's true and hopefully reach a contradiction. So again, we would say, and we don't need to do this instantiation part. Actually, I'm going to do both instantiations, existential instantiations of C and K right in the beginning. So I'm going to say for all x greater than or equal to B, 3x plus 1 is greater than or equal to A times x squared. And so I'm going to say existential instantiation of my assumption. So I'm skipping a step here. So this part here would be my assumption, and then I would jump into the existential instantiations. And I did 2 of them at once. Just be careful when you do stuff like that. Right, so now I want to, so if I divide both sides by x squared, I would get 3 over x plus 1 over x squared is greater than or equal to A, right? So that's math. Divide all terms by x squared. Now, here's the sort of the tricky part, though. So I want to prove that I can choose some value of x that makes this false. But what I'm going to do instead is I'm going to implicitly use the limits. And why is because otherwise I have to do a case analysis. So I would have to do a case analysis for analysis. So if A is greater than 1, greater than or equal to 1, and A is less than 1. So A, because then this function behaves differently, and I have to choose different values for this. So what I do know is that I can make 3x plus 1x squared as arbitrarily small as I like. So I know there exists some value k such that for all x greater than or equal to k, 3 over x plus 1 over x squared is less than a. So I know this because I know about limits. And even though, I mean, it's a sort of an interesting exercise to try and find values, specific values of a that, or that I can substitute in for x that make this true or false. For instance, if I know that a is greater than or equal to 1, then it's no problem to choose a value x that makes, so, you know, I can choose, if a is equal to 1 or greater than or equal to 1, then I can choose x equal to 4, right? And then, so I have 3/4 plus 1/16, which is less than 1, right? But then I have to say, well, then I have to do this other case as well. So it's okay at this point to say that, well, using our knowledge of limits, I can always choose some value for x that makes this less than some constant, right? So then, yeah. So so yeah, I shouldn't write this actually. I would say greater than or equal to a, and then I would say that that's a contradiction. That's false. So 3, what is it? 3x, sorry, 3x plus 1 is not omega of x squared. And that is a bit hand wavy, but it's, I mean, once you reach this point, it's fine because you can make that expression as small as you like. All right. So good. Any questions on that? Okay. So even though, and then you can of course do that with the limits as well. So with limits, this becomes even easier. Let's say, or not easier, but I guess more straightforward. So I could say 3x plus 1 is omega x squared if and only if the limit as x approaches infinity of 3x plus 1 over x squared is not equal to 0. Right, so this, if you recall, this was one of our definitions. However, it's pretty easy to see. So the limit of x as x approaches infinity of, so I can say cancel out my x term plus 1 over x squared. That is actually equal to 0. So right away, using limits, I've gotten a contradiction, right? So therefore, 3x plus 1 is not big omega of x squared. Okay, and I can, and as I said, you know, we could do more formally. I could use this as a statement that I've assumed to be true, and then this is something I've proven to be true, and then I can use conjunction to put them together and more formally reach a contradiction. But for this big O and big omega notation, you don't have to do that. Just do the math and declare, if you have some constants to declare like your C or your K, make sure you declare them specifically and show, you know, show all your work, all your mathematical work. But you can skip the formal steps, the existential instantiation and all that other stuff. That's not necessary. Okay. Any other questions or Does anybody want me to go through more examples, or are we comfortable with this? Yeah, okay. Pretty straightforward at this point. All right. So that brings us to the last thing, which is Big-Theta notation. So again, f and g are functions. So f of x is theta of g of x if f of x is O of g of x and f of x is big omega of g of x. So if both of those things are true, then we say that that it's a tight bound. Right? So f of x is said to be big theta of g of x. Equivalently, f of x is, you know, a member of the set of the tight functions g of x. So f of x, another way to say it is f of x is big omega of g of x if and only if there exists two constants or three constants greater than 0, such that for all x greater than or equal to k, and there should be a 0 less than, this f of x falls in between the constant c1 times g of x and the constant c2 times g of x, right? So that's just sort of, if I combine this statement here, or the proofs, or the the definitions of big O and big theta, if I combine them into one sort of statement, then I get this. And I can also use limits to say that it just solves two problems in one. Yeah, it expresses two problems in one. You still have to solve big O and big theta. You have to prove both of those things. So if I want to prove big theta, then I prove that it's big O. So we'll go through an example in a second. But you do have to prove both big O and big omega. But yeah, you can sort of roll the steps up, but it's really no different because I have to prove each of these inequalities separately. You can't really do them both at the same time. And using limits just means that there's some C1 and C2 where the limit as x approaches infinity falls between those two constants. And yeah, another way, I think an equivalent way to write that, I would have to look this up, though. I'm pretty sure. Actually, I'll look it up. I won't give you something that might be false. All right. So yeah, so big O is to functions as less than or equal to is to numbers, and greater than or equal to numbers is as big theta, and equal is sort of the big, or sorry, this is big omega and this is big theta. So that's one way to think about them. And so if I wanted to prove, say, 3x squared plus 2x plus 1 is big theta of x squared, then I would show, I would first show that 3x squared plus 2x plus 1 is big O of x squared. And to do that, I would say, well, 3x squared plus 2x plus 1 is less than or equal to 3x squared plus 2x squared plus x squared for all x greater than or equal to 1, less than or equal to 6x squared. So this function is O of x squared with witnesses c equal to 6 and k equal to 1. And then I would say, well, 3x squared plus 2x plus 1 is big omega of x squared. And that's, I'm really not good at writing this omega. So that means 3x squared plus 2x plus 1 is greater than or equal to 3x squared for all x greater than or equal to 1. So therefore, 3x squared plus 2x plus 1 is omega of x squared with C equal to 3 and K equal to 1. No. Let me think. No. The same K? No, you just have to prove no, because you can just take the greater of the two Ks. So you can use different Ks for each of them. If you happen to get different Ks, then your sort of ultimate K is the larger of the two. Right, so that means we have our C1 is equal to 3, C2 is equal to 6, and K is equal to 1. So yeah, 3x squared plus 2x plus 1 is big theta of x squared with these witnesses. So I just wrote that a little bit backwards, but that's, yeah. Good. So that's just basically putting those two other things together. All right, any questions? All right. So that's, I mean, these are good things to know because big O comes up a lot in computer science. And if you write an algorithm, you'll probably be asked to justify the runtime in terms of big O, and you would do it exactly like this. You would find some C and some K, or use limits, or, you know, at some point, all this becomes informal. And if it's a very simple function like this, you can just immediately say, well, that's, you know, it's x squared and that's tight. But there's, you know, more complex functions where it's not that simple. So it's good to know these techniques. All right. But if that's that, I'm going to move on to the next lesson, which is functions. So we've been talking a lot about functions here, but so we're going to talk a little bit more about them in depth. So we've been using them for this big O and big theta. All right. Okay, so we're going to start with some slides and then move into, and then we'll jump into OneNote when we start to get into the examples. So this is introduction to functions. Part of this we've already seen. We'll review it very quickly. Again, these are based on slides by Dr. Robert Collier. I've modified them, so if you find any mistakes, they are almost definitely mine. Okay. So this is a review. We saw this at the beginning of the big O stuff. A function is analogous to some subprogram written to accomplish a specific task. And the thing we know about computers is they do exactly what they're told. So anytime you give them an input, the output is going to be well-defined. All right, so more generally, a function is a map that specifies a return value. That's one return value that's associated with each argument. So yeah, so functions are described with respect to of a set of possible inputs to a set of possible outputs. So that should be pretty straightforward. This is something we saw before. The Gregorian calendar is a leap year function. So if we, if we wanted to compute if a certain year is a leap year, then this will do it for us, and it'll return either true or false. And this is, we reviewed that earlier. So these are, you know, it's just a mapping from the years to either true, yes, it is a leap year, or false, no, it's not a leap year. All right. And this is where sort of, so this is a new material here. So that is a review of the things we've went over twice now. So if f is a function from a to b, we can write it as f colon a arrow to b. So where a and b are sets. And so we can write f with a in brackets equal to b to indicate that b, that's an element of the set b, is the unique element assigned by the function f to the element a, where a is the member of the set big A. All right, so that's sort of the formal definitions. We'll go through a lot of examples of what exactly makes a function. But first, some terminology. So for a function from the set A to the set B, we call the set A the domain of f, and the set B is the codomain of f, right? So in a sense, the set A is the inputs and the set B is the outputs. So domain equals input and codomain equals output. Some more terminology. If we take some specific element of A, so A is a member of the set A and B is a member of the set B, then B is the image of A and A is the pre-image of B. And the set of all the images of the elements from the set A, so that means all the elements that are mapped to by the function f is called the range of f. So these are all the possible outputs of my function. All right, so I might have my set B might contain more elements that are never mapped to by our function f. All right, so this is a function. So for people born in the fall and what month they were born in. So then what is the domain and codomain and range of f? What is the image of Rob? Let's go jump back to OneNote here to explore this. Okay. So what is the domain of f? All right, so anybody, what's the domain? Everybody remember the definitions? Set on the left. Yeah, so it's the set of inputs, so to speak. So the domain is the set Rob, John, Mary. Ooh, what happened? Okay. So I think my OneNote has. This was doing this earlier, and it has a bug. Let's see if I can type. Richard. All right. So I'm gonna have to do without the stylus, but that's fine. It should still work. So what is the codomain of f? Yeah. It's the set, yeah. The set months of fall. Oops. And so what is the range of f? Anybody remember that? It's not months of the fall. It's a subset of months of the fall, right? It's September, October, December. Yeah. So notice that nobody maps to November. So we have September, and I'll just do the short forms. October and December is the range of F. So for any given output, these three are my possible, or for any given input, these three are my possible outputs. That's the range. So image of Rob is what? Image of Rob is October, yeah. Pre-image of September. Yeah, Mary. Yeah. So the pre-image is Mary. Pre-image of December. Yeah, so now I got two. Yeah, Richard and John. So it's not defined as a set. So we actually have two distinct pre-images of December. Okay. Yeah, we got that. All right, so if S is a subset of the domain, then the image of S is the subset of the codomain that contains the image of every element of the subset S. Right, so I can take, I could define the function F on some subset of my domain, and then the codomain, yeah. The image is defined as a set that is sort of equivalent to the range of that subset. Right. So if a subset of people born in the fall, S is Rob and John, then the function F of the set S is equal to the set October, December. Right. So that's simply the range of that subset. Okay. All right. Any questions on, so that's just terminology. That's, hopefully that's all straightforward, but are there any questions? All right, yeah, that's such a pain. That's, all right, so function F is an injection or an injective function if my two images being equal implies that my two pre-images are equal. So what does this actually mean? If a function is an injection, then every element of the range has exactly one pre-image that maps to it. So injective functions are said to be one-to-one. Alternatively, so this is the, oh my goodness, what a pain that is. Both pens. Okay. Alternatively, a function is an injective function if we take the contrapositive. So if we take the contrapositive of this definition, so this is an implication, then the contrapositive means that if my two images aren't, or if my two pre-images are not equal, then my two images are not equal. Alternatively, if we did this, we did implication equivalence, we would say that X equals Y, and then or F of X is not equal to F of Y. So either my two images are the same, or my two pre-images are the same, or my two images are different. So yeah, I'm kind of in a bind. So I can't really use my stylus because it's blinking out my computer. And to fix that, I have to restart my computer. So no, it's just it's some bug that just cropped up today, actually. But I thought I restarted it and I thought it was gone for good, but now it's back. So I might switch back to the. I'm going to switch back to the slides. The slides are not as expressive as when I'm drawing, but it's better than nothing at this point. It's too bad. I wonder if there's something else I can use. Maybe I can use a whiteboard or something. Then I got to switch back and forth. So yeah, sorry, that's yeah. I'm just going to switch back to the slides. It's a shame. It's not as good, but it's better than nothing. All right, let's go back to where we were. Yeah, so an injective function is said to be one-to-one. Maybe I can use my let's see if this works. So 1, 2, 3, 4, 5. So an injective function means that each item of the domain or the codomain is mapped to at most once. So this would be an injective function, right? Because for any given member of my codomain has at most one pre-image. Okay, does that make sense? You guys can all see this whiteboard, right? All right, perfect. Oh, better than nothing. So yeah. So what if I did? If I did this, now is this still an injective function? No, it's not, right? Because my 3, it has two pre-images. It has a B and a D. So f of B equals f of D equals 3. Right, and if that's the case, then it's supposed to be that B is equal to D, but that's not the case. So that's the definition of injective function. What if I did this? Actually, is that an injective function? Not a function. Very good. Yes. So D is mapped to 2 separate elements, so that's not a function. So now this is back to being an injective function. Let's see. How do I exit out of here? Cool. All right. That works. So injective functions are said to be one-to-one, and they're one-to-one because is a function, so I'm mapping from at most one, and I'm specifically saying that I'm mapping to at most one image. So a function is an injection if no two distinct pre-images map to the same image. So to demonstrate that a function is injective, we either assume that our two images are the same and show that the pre-images are the same, or we assume that our pre-images are not the same, and that implies that our images are not the same. So we want to prove or disprove these things. My goodness. All right. So just let me get set up here. Okay, so let's go back to our whiteboard. So we want to prove or disprove that f of x equals 2x plus 5 is injective. And our definition is that for all x and y, f of x equals f of y implies that x equals y. Okay, so what we're going to do is so we'll universally instantiate two items. So this is on this is a map from the real numbers to the real numbers. So I'm going to instantiate two arbitrary items, and I'm going to assume that their this part is true, so that their images are equal. So f of x equals f of y, and this is our assumption. And that implies that 2x plus 5 equals 2y plus 5. And that's just 1, 2 in math. And then we can, so I'm running out of space here, so I'm going to skip the algebra. And it should be pretty clear if we subtract 5 from both sides and divide both sides by 2, that we get down to x equal to y. So that's 4 in math. So we've proven what we wanted to prove, that so we've taken two arbitrary elements and shown that if their images are equal, then their pre-images must be equal. So then 2x plus 5 is an injective function, or an injective. Okay. Good, clear questions? All right. So let's look at g of x is equal to 0. And g is a function from the set of integers to the set of integers. So if g, oh, damn it. Yeah, all right. If g of x, so g of x is equal to 0 is our function, is injective, then x not equal to y. So if we take the contrapositive, implies that g of x is not equal to g of y. Okay. So we're going to instantiate two items from the set of integers, so an x and a y that's not equal to x. And then we're going to say that g of x equals 0, g of y is equal to 0. So this is just the definition of g of x. So g of x equals g of y. And this is actually a contradiction to what we wanted to prove. So this is not injective. Okay. So we're using a slightly different proof technique, and I'm shorthanding a lot of this because I have limited space. I can't scroll anymore, but does everybody get the idea behind that? So if you try one sort of proof and that doesn't work, maybe try the contrapositive. And in this case, we did contrapositive, and if I had set it up better, it would have been a proof by contradiction as well, but like I said, I'm shorthanding it here. Okay. And then our last one, h of x is equal to the absolute value of x. So we want to show, is it injective? So for all x and y, h of x equals h of y implies x is equal to y. But we can take two instances, so -1 and 1. So this is universal instantiation. So now 3, we know that h of -1 is equal to h of 1. And this is just 1, 2, and math. And then we can use, so we assume this to be true, so we could use, say, modus ponens to say that, well, h of x and h of equals h of y implies that x equals y, so we get -1 is equal to 1, which is, of course, false. So we reached a contradiction. So h of x is not injective. Okay. Clear? Questions? Okay. So that's injective. Now we're going to look at something similar, surjective. So a function f is a surjection or a surjective function if for all b element of b, there exists an a element of a such that f of a is equal to b. So what does that mean? Function is a surjection if every element of the codomain has at least one pre-image, or equivalently, the range and the codomain are equal. And surjective functions are said to be onto. So let's take a look again at A, B, C, D. So this is a surjective function. And why is this a surjective function? Because every image has a pre-image, or every member of the codomain has a pre-image. therefore surjective. Right, so if I did something like this now, is that surjective? Right, so it's not. It's because 2 has nobody mapped to it. Incidentally, is this injective? No, right, because we have 2 images mapping, or 2 pre-images mapping to our image of 3. So no. Okay, so everybody understands what surjective is? The domain and the codomain, or the codomain and the range are equal. So to demonstrate that a function is surjective, you must start with an arbitrary element of the codomain and show that there exists some member of the domain such that A is mapped to B. So to demonstrate that a function is not surjective, we find a specific element B such that there's no pre-image of that element. So such that there is no such element where that is true. So let's look back at our old functions here. We proved that the injectivity of them, so let's prove the surjectivity of them. So we're going to take the function f of x is equal to 2x plus 5. So we're going to use a little bit of algebra and say that we're going to solve for x. So x is equal to f of x minus 5 over 2. So these are 2 equivalent expressions that are different only by algebra. So then I'm going to universally instantiate some element of the real numbers. So that's a universal instantiation, and it's an arbitrary. So we didn't choose a specific element. We've chosen some variable. It could be any member of the reals. So then we're going to let x equal b minus 5 over 2. And we know that x is a member of the real numbers. That's simply math. We haven't done anything that made this not real because b is a real number. So if we take f of x is equal to 2x plus 5, so it's equal to 2 times b minus 5 over 2 plus 5. And if you do the cancellation and subtract and add our 5, then we get that equal to b. So therefore, since b is an arbitrary member of the real numbers, we can do a universal generalization. So for all b element of the reals, if x is equal to b minus 5 over 2, then f of x is equal to b. And that's a universal generalization. And then we could do existential generalization, although I'm running out of space. So we've shown that for any given b, there is an x, so that's universal or existential instantiation, therefore there must exist an x, but I've run out of space. So that means that f of x is surjective. Good. Questions? All right. This is all taken longer than I thought, but that's all right. So what else? G of x is equal to 0. Let's sort of do this. I'm going to skip much of the formal techniques and just sort of show the logic behind it. So g is a function of the integers to the integers, where g of x is equal to 0. To show it's not surjective, so that's what we want to show, we will take the negation of the, for all b element of the integers, there exists an x element of the integers, where f of x is equal to b. So I'm taking the negation of the definition of surjective, and then if you recall how to do the negation, so I'd say there exists a b such that there does not exist an x element of the integers where f of x is equal to b. So I've flipped my quantifier and I've moved the negation inward. So I do that again. There exists a b such that for all x, f of x is not equal to b. So this is what I want to show. So I want to find, so I could take 7 is a member of the integers. So that's my existential instantiation of b. And then we know that for all x, g of x is equal to 0, which means that for all x, g of x is not equal to 7. So therefore, g of x is not surjective. Right, because we found element b that nothing maps to. Okay. Questions? All right, and our last one is, can I just clear this? Oh, good. So our last one is 8, whoops. Come on, man. All right, I'll try it one more time again. All right, I don't know what's going on with my computer today. So for h of x is equal to, oh, is that, yeah, okay, try unhiding. Ah, perfect, well done. So yeah, what's my function now? I did the equals 0, so this is, sorry, h of x. And is equal to the absolute value of x, and is that surjective? So if it's not surjective, then there exists some element of b that for all x, h of x is not equal to b. Right? So there's some member of the codomain that's not mapped to. So for instance, we could take -1 is the element of using a universal instantiation. So it's a member of the integers. And we know that for all x, h of x is greater than or equal to 0. So therefore, for all x, h of x is not equal to -1. So we found our b that shows that h of x is not surjective. All right, questions? Okay. All right, so if a function is injective, then each element of the codomain is mapped from at most one preimage in the domain. And if it's surjective, then each element of the codomain is mapped from at least one preimage of the domain. So what if a function is both injective and surjective? What does that mean? So let's see. Injective and surjective. So I have A, B, C, D. 1, 2, 3, 4. So each element is mapped to by at most one and at least one. Right? So each element of the domain has exactly one preimage or codomain. Right? So this is what's called bijection or a bijective function. So it is both one-to-one and onto. All right, so bijections are sort of, in a sense, easy to identify because there's simply one arrow from each preimage to each image or each element of the domain. So yes, a function is both injective and surjective is known as a bijective function. So to just demonstrate that a function is bijective, we have to demonstrate both of these things. Both that is, demonstrate that it is injective and also that it is surjective. Right, so if we have this function here where our domain is w, x, y, z, and our codomain is 0, 1, 4, 9, is this an injection? So injection is one-to-one. So remember the definitions. Is this an injection? No. So what is it that, what's the reason why it's not an injection? Yeah, so there's two different things that map to one. So we have f of x equals f of z equals 1. So not an injection. Is it surjective? And why? So not surjective. So why is it not surjective? 9 has no preimage, right? So nothing maps to 9. So it is not injective, it's not surjective. So then is it bijective? Yeah, so that means it can't be bijective. Good, very good. What about this function now? So is this an injection? Is this a one-to-one? Yes. So it's an injection because each element of the codomain has at most one pre-image. Is it a surjection? Yes, it is in fact a bijection. But yeah, it's a surjection as well because every element of the codomain is mapped to, which means that it's a bijection. Okay, is that clear? Any questions on that? All right. Function, if a function f is a bijection, then f is invertible with an inverse function f to the -1. So I'll just call it inverse function, such that the inverse function, if we map, if we supply it with an image of the original function, it maps back to the pre-image, right? So this means that if I went back to my white screen here, 1, 2, 3, 4, A, B, C, D. So if I had some mapping, and let's say it's just very straightforward, then an inverse, if this is the function f, then the inverse function is takes A, gives back 1. So it basically just reverses these arrows. Right. But if we do that, it might not necessarily be a function. So why is it necessary for a function to be a bijection in order for it to be invertible? So let's walk through some of the proofs. So we're going to prove this part, and then we'll end on that. All right. Well, let's walk through. Yeah, because everything has something back to, but why is it not a function if it's not a bijection? Like, so why is, I guess the question is, what is happening here? Yeah. So there's a few different reasons. So we're going to explore basically why that's the case. I guess with some formality, and I'm going to rather than try and fit all this into the white screen. So this is less than ideal, but let's walk through this proof. So yeah, this is the definition of a. This is not injective. Right, so this is the definition of injective, and we've negated that. So we're saying if something is not injective, then why is the inverse function not a function? Or why is the inverse of the function not a function? So to take the negation of a quantifier, we flip the quantifier and move the negation inward. So we do that twice, and now we have the negation of this implication. Yeah, so now we use the implication equivalence. I don't like. Well, we started. We'll finish on this. I don't really like. I would have preferred to. I was going to write this out on OneNote, but that didn't work out. So yeah, and it's better if I explore this line by line, but I didn't set it up that way. So now we're going through all this clutter. So if there's any step that you don't understand, please let me know. So this is simply implication equivalence. So we've taken the negation of f of x is equal to f of y. But then when we apply the De Morgan's law, we basically get this double negation here, and we flip this or to an and then we take the negation here. So this double negation cancels out. So we have f of x is equal to f of y, and we can take the negation here. So if it's not injective, then there exists an x and a y such that f of x is equal to f of y and x is not equal to y. Okay, so why is that a problem? So we're going to do an existential instantiation. So let u equal f of I, which is also equal to f of j, right? Because these two things are equivalent. So then when we take the inverse function, so this is the original function, we take the inverse function, it maps to I in this case, but it also maps to j. So yeah, somebody mentioned it earlier. We end up with two images if it's not injective. So when we invert the function, we end up with two images. All right, so that's sort of, yeah, sorry for the clunky presentation. Hopefully you sort of understood. Basically, that's the formal way to say that if you invert a function that's not injective, you end up with two images. And therefore, it's not a function. So let's assume that f is not a surjective function. So then this is the definition of surjective, and we're going to negate it again. So this should all be fairly straightforward. As we walk it in, we flip the sign, and then eventually we negate the original premise. So there exists a B element of the codomain such that for all elements of the domain, f of A does not map to that B. So that's, if it's not surjective, that's the case. So that means that on the inverse, hey, that's weird. So on the inverse of this, if we take f negative 1 of B, we end up pointing at nothing, right? So this is not, since it has no pre-image, then the inverse of the function means that it has no image, okay? Good questions? Again, this is a bit of a clunkier presentation than I intended, but right, and this is sort of the explanation of that. All right, and then, wow, this will take much longer than I thought. We're going to go through the whole 3 hours tonight. So given functions f and g, the output of one and the input of the other can create a new function. So this is sort of analogous to if I take in computer science, if I had two methods or two functions, so let's say I had absolute value that took some argument, and then I passed it, some other function which is power A2. So I can sort of pass one function into another function, assuming this is Python, and I can compose those two functions. So when we talk mathematical functions, we do something similar. So if I have a mapping from B to C and a mapping from A to B, then I can compose these two functions. So the way it's written is sort of backwards. So it f dot g means f follows g, which means that we first do the function g and then we do the function f. Similar to how we did it in if we had a Python program. So we would first evaluate g of x and then use whatever the answer is to evaluate f of x. Right, and that's, we could see that quite simply if we did 3 A, B, C, 1, 2, 3. So this is some function, nice one-to-one, and this would be our function g. And then we take the input from G and pass it to F. So then FOG of 1 is equal to 1, right? So we follow first the evaluate G, and then we evaluate F. And yeah, if we had if we had mathematical expressions as our functions, then we just simply pass this argument in. So we substitute 5x plus 3 for the argument for f. So this gets substituted for x, and we evaluate it. So f follows g of x, in this case, is 20x plus 13. Okay. And if we did the opposite, so if we did g follows from f, we would get g of f of x, which is equal to 4x plus 1 plus 3, 20x plus 8, right? So, so f follows g is not necessarily equal to g follows f. Questions? So what happens if we create a composition between an invertible function and its inverse? Any guesses? So if I take f of minus 1 of x, what does that give me? X, yeah. So that simply maps back to the original input. All right, I think this is the last slide. So can we define a bijection between these functions? So if I have a domain of x, y, z and a codomain of 0, 1, 4, 9, can I have a bijection there? So bijection means 1-to-1 and onto. No. And specifically, so if I sort of sneak this in the side here, 0, 1, 4, 9. So it has to be 1-to-1. So if it is 1-to-1, then it's not onto. And if it's onto, then it's not 1-to-1. Sorry. Actually, that's not even, you're not allowed to do that in a function. Yeah, exactly. So, and the same thing if we try to do it here, in this case, so in this case, we can do 1-to-1, but we can't do onto. In this case, we can do onto x, y, sorry, w, x, y, z, 0, 1, 4. We can do an onto function, but we can't do 1-to-1 because the cardinality is not the same. So in order for it to be a bijection, the sets have to have the same cardinality. So I need 1, 2, 3, A, B, C. If I have the same number of elements in the domain and the codomain, then I can have a bijection. It's not necessarily a bijection, but it can be. Otherwise, it cannot. All right. Questions? All right, that's it for tonight. Well, that went longer than I thought, and sorry for the technical difficulties. I'll try and get those worked out. Same as always, I'll stick around for 10 minutes for questions, and yeah, that's it for tonight.